the LEDs on. We're going to use them again. But now I want to talk about this idea of mapping bits to decimal numbers. Okay, so when we count, we have 10 fingers. So for us, it's very natural to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we loop around 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. You start over again, 21, 22. Actually, it's funny because I have a 4-year-old daughter, and just last night, she got so excited because she counted to 121. And she got stuck at 121. Going to 122 for whatever reason was hard. But that's great progress compared to where she was, where she could only go up to like 19. Because something clicked and she understood the way that our number system is structured and that you have this repetition. So this is called the base of our number system is 10, which means we go from 0 to 9 and then we repeat. So there's 10 numbers. Okay, with bits, it's not 10, it's base 2 because you just have 0 and 1. Okay, so if we need to talk to computers and we need to tell them numbers, we have to convert from our decimal way of describing numbers into the bit or binary way of describing numbers. Okay, and so the way that this works, let's get rid of this for a moment. So this is known as binary notation. And so this is decimal notation. Actually, I'm going to write it on the other side. So decimal notation. Okay. So we have numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, these are the building blocks of our decimal notation. And now we want to convert these into some binary number. And binary, we only have access to zeros and ones. Okay, so this is the conversion. Sorry, I'm making this table bigger than it needs to be. Like this. So for 0, we just put a 0 like this. All right. For 1, it's 1. For 2, now we don't have a number 2 here, right? In bits, we just have 0 and 1s. So the way that we write this is 1, 0. Okay? And if you want to, I don't want to get into too much depth here just because of the way we're limited in time, but the way to think about this, like when you write out a number, say 365, okay? You remember how this works, that this is called the ones place? Ones place. This is called the tens place. And this is called the hundredths place. Right. So what are we doing here? Each time we go to another place, we're multiplying by a factor of 10. Okay? And binary, we have the exact same way of doing this, except each time we move to a different place, we multiply by a factor of not 10, but 2. So here, this would be the ones place. This would be the 2 place. 2's place. This would be the 4th place, if we kept going, the 8th place, the 16th place, 32nd, 64th, etc. So because this is the 2's place, so 2, 0, so that's 2, right? So we do 2, there's nothing left in the 1 place, so 2 plus 0 is 2. This is why this is 2. Okay. For 3, we want to have a 2th place, 1 in the 2, and then we want to add a 1 in the 1 place. So this is 1, 1. For 4, now we just want to have 1 in the 4th place. So we would go 1, 0, 0. For 5, we have 1 in the 4 place, 0 in the 2, and 1 in the 1 place. So it's 4 plus 1 is 5. 6, I think of 6 as 4 plus 2. So it's 1, 1, 0. 7 is 4 plus 2 plus 1. So this is 1, 1, 1. 8, I just have 1 in the 8th place because 8 is a power of 2. So it's 1, 0, 0, 0. And then 9 would be, I have my 8, and then I have 1 more in the 1th place, like that. Okay. So now what we'll do is, so this is only has, to keep everything like the same length, we can just add some zeros on at the end here, like this. Like this. Okay, and so now we've written out the binary representation of the decimal numbers 0 through 9. Okay, and so we see we need 4 bits. So 1, 2, 3, 4. In total, we need 4 bits to represent the numbers 0 through 9. Any questions on this? This is kind of, I went fast here, but this is just the basic kind of ideas of going between binary and decimal. Okay, so now the last activity we're going to do, and this is the challenge for you guys, we're going to use our circuit here. Leave the lights on and clear out the logic gates. So bring these guys back here. Okay, get rid of all the wires. All right, and now your challenge is to do the following. Okay? Wire the lights in such a way that, so let's just focus on rows 1 and 2. Okay, so I'm going to erase everything else. All right, so I just want to focus on rows 1 and 2. And now these are just 2 bits here. So I want to, again, interpret this as our inputs x and y. So x, y, like this. And so this would be 0, 1, 1, 0. And so I want you guys to try to come up with some circuit here such that this truth table is satisfied. So when x is off and y is on, it displays the number 1 here. And when x is 1 and y is 0, it displays the number 2. And I guess there's some ambiguity on how 1 can be displayed, right? You could put it all here or that column. Have your pick.
It's usually the right column.
Is it?
Yeah.
Okay, good. Okay, so the 1 will be on the right column.
Usually I think it was like a 1.
Yeah, for 7-digit display, it's on the right side.
Yeah, but that, yeah. Okay.
15-digit column.
So I'll give you a hint. First of all, there's not one way to do this. There are many different solutions to this. Here's one hint toward one solution. Remember how and behaves.
Yeah, I wrote it down. So I'm
Right.
gonna look at and.
So x and y. This has the property that it's always off.
It's always off the stuff with both conditions.
Yep, exactly.
So I didn't, wasn't gonna look at that.
You got the one right? Okay.
You said the one has to be on the right, correct?
Yes.
Okay.
Okay. Yeah. Let's see. Oh wow.
When both, oh, this is not it.
Okay,
When
okay.
both are off is 1, and then when 1 is on, it's 0. And when just this one is on 3, and like when both of them are, I'm trying to do that. So I managed to,
You try. Wait. What do you want to
I
happen?
want both on to be 2.
To be 2.
So I
Okay.
managed to do like, when one of them is on, so because of this one, I figured you need it for 1, 0, and 3,
Okay.
but not for 2.
So when they're both on,
Yeah, so,
then you want this middle one to go, right?
yeah, so,
So what you could do is you could, and that looks a lot like this, right? This is saying that when they're both on, you have that. So if you hook them both up to an and then you plug that to the middle one, you'll get what you want.
what I was struggling with was
Yeah.
actually these two. Because these two, I needed for 0,
Okay.
so I needed just for like this one. So not, so I want it to be on when this is on, but not when both of them are on. You see what I mean?
Gotcha. I gotcha.
Yeah, so how do I do that? It was not Y or, so do I have to do like not Y
Yep. And then and it, right? So
and?
yep.
Okay,
There you go. Okay, let me give you the solution for the first one. And actually, this is a general rule of thumb or a general prescription. If you want to build up any truth table, you can do it using this method. So you see, what we want is when x is 0 and y is 1, we want this to be on. We want it to display 1, right? Another way of saying this is that instead of x being 0, we have not x is equal to 1. Right? When x is 0, that means that not x is 1. Right? So then what the way to interpret this row is saying is that when not x is 1 and y is 1, we want it to display the number 1. And that looks a lot like this and here, right? Because now you have two things being 1, and you're displaying 1 here. So what you can do then is you bring up the NOT gate here. Okay, so now this is what's coming out of there is not x. And so then if I bring in an AND, I'm ANDing together y and not x. And now I want this to hook up to all of the lights on the right, right? Because that's the number 1. Just like that. Yeah.
We put N for this, and it was only turning on for both of them on. What I actually needed when either only this one is on
Yeah.
or both of them on. Then how do I do it?
Oh, then you could do an OR gate or an XOR. Wait, what did you want?
So I wanted like this to be on only when this one.
Oh,
is
just
on
hook it right up?
or both of them on. So I needed for two.
Oh.
Two of the.
Well, when you could directly hook from here to here, right? Then that would could be controlled by this, right?
Oh. Okay. Yeah. Okay. So.
Yeah. Okay, so this gives us 1, and now to do 2, you could do the same thing. The way to think of this is that. So in this case, not y. Maybe it's a little misleading how I wrote this. Well, for this row, when y is 0, that means that not y is 1. Let's see. Okay, I think it's right like this. So not y is 0 here, and not y is 1, like this. So now what we can take in order to get these guys to light up, the number 2, we could take not y and it with x, right? And then hook that up to each of the bulbs for the number 2. So if we bring out another NOT gate, and we do, now we want not y, like that. And we want to AND it with x, like this. Okay, good. So we have the not y here, ANDed with x, and now we hook it up to all the bulbs that give us 2.
If you hook it up to the same ones that gave you 1, the ones that gave you 1 disappear.
Oh, they do? Oh. Okay. But I don't think that matters. Let's see.
See how the other
Oh.
goes away when you do
Okay. Yes.
it? You get a 2, like it'll
All right, so then what we need to do is, all right, so now what we do, so whenever there's a repeat, we have to hook it up to an OR. All right, because then it's going to take either one. All right, so if it has a double, sorry, I didn't know it did that. So I guess it's those guys. Yeah, and then you'd put an or. So let me finish doing this. In this case, it won't matter.
Any numbers shared by both.
Right, if either one is on, we want those. Or if they're both on, we want.
The ones that are.
Yeah, any one. So I guess there's 3 of those, right? Is that? Yeah, these 3. So there should be 3 bulbs that are connected to an OR gate.
Top, middle, and bottom of the right side.
Yes. There you go. And one of the things that people do in circuit design is try to simplify this as much as possible. Right? So clearly you need a wire that's going to every light bulb, right? That is for sure. If those light bulbs are going to be used, we need a wire that goes to it. But all the logic that goes prior to that, there are ways of simplifying it. Now I don't know if actually this circuit can be. There might be a simpler way of doing it. But believe it or not, this isn't too complex. I know it looks complicated. Right. Yeah, this one should. So this is 1 and then 2. Oh, I missed one. Sorry. Oh, the bottom one is shared too. Ah. That one shared as well. Yeah, so there's 4 bulbs that are shared. These 3 and then that bottom one. Okay. All right, so I think that's pretty much all that I wanted to talk about. Now, this is great because the simulator, you can pull it up anytime you want. And in the book, there's more elaborate exercises. I don't know if you're going to end up building the half adder. I'm not sure what the plans are for. Do you know what, are they going to? Oh, great. Okay. So you will have more advanced implementations of these ideas. Good. Yeah, this was a lot of fun. Yeah. Right. So on the board, remember we wrote down the numbers to 9, and we ended up needing 4 bits. So you need 4 toggles. Yeah. Right, you can go up to 16, but you have to have, because if you had 3, you can only go up to 8, right? So, or sorry, you can only go up to 7 because you need, the 4th one gives you 8, and then, so the 9 would be like 9 is 1, 0, 0, 1, right? Yeah, we start counting from 0 when you're doing binary. First number is 0. It's a little different.